Hello, welcome to ICCP Online Learning. For today's video, we're going to discuss about Chapter 2 Other Integration Concept Formula. On our previous lesson, we discussed about the basic rule of the integration. But now, we have a different or other concept and formula for the integration. We have the inverse trigonometric function, and the following integration formulas yield inverse trigonometric function. So we have the integral of du over the square root of a squared minus 2 squared, that is equal to sine -1 times the u over a plus c. We have also the integral of the du over a squared plus u squared, that is equal to 1 over a tangent -1 times u over a plus c. We have also the integral of the du over u times the square root of 2 squared minus a squared, that is equal to 1 over a arc secant times the absolute value of u over a plus c. So let's have the example. So in this example, we have the integral of du over the square root of 9 minus x squared. So in this example, we're going to use the u substitution. So our u is the x and the du is the a dx. So as you can see on our table, on the upper right side, as you observe our given, it is the same as the first integration formula. Okay, that is equal to arc sine of 2 over a plus c. So because of our u is equal to x, we're going to substitute that into x. Then our a is 3. So we have the arc sine of x over 3 plus c. On the second example, evaluate the integral of the dx over the square root of 4 minus 9x squared. So we're going to use also the u substitution. So our u is equal to 3x and our du is equal to 3 dx. Then here, it is the same with the first integration formula and written on our upper right side. So we have the 1/3 integral of du over square root of 4 minus u replaced as the 3x squared. By getting the integral of this part, we have the arc sine of u over 2 plus c. Then substitute the value of u, and that is 3x. So the final answer is 1/3 arc sine of 3x over 2 plus c. On the hyperbolic function, and we have 8 hyperbolic function based on our slide. So we have the integral of the hyperbolic sine u du, that is equal to hyperbolic cosine u plus c. We have also the integral of the hyperbolic cosine u du, and that is equal to hyperbolic sine u plus c. We have the integral of the hyperbolic tangent u du, that is equal to the ln of the hyperbolic cosine u plus c. And 4, we have the integral of the hyperbolic cotangent u du, and that is equal to the ln of the hyperbolic sine u plus c. And we have also the integral of the hyperbolic secant squared u du, and that is equal to the hyperbolic tangent u plus c. And we have also the integral of the hyperbolic cosecant squared u du, and that is equal to negative hyperbolic cotangent u plus c. We have also the integral of the hyperbolic secant u hyperbolic tangent u du, that is equal to negative hyperbolic secant u plus c. And lastly, the hyperbolic or the integral of the hyperbolic cosecant u times the hyperbolic cotangent u du is equal to the negative hyperbolic cosecant u plus c. So here, under the hyperbolic function, we define in terms of the exponential functions. So we have 6 and hyperbolic functions in the terms of the exponential function. And we have also since the hyperbolic functions are expressed in terms of e raised to x and e raised to negative x, we can easily derive rules for their differentiation in integrations. And there are the following. So we have for the prime of the hyperbolic sine x, that is equal to hyperbolic cosine x. We have for the integral of the hyperbolic cosine x dx. And we have also for the prime of the hyperbolic cosine x, the cotangent, the cosecant, and the secant. And these are the other form of the hyperbolic integration. So in certain cases, the integrals of the hyperbolic functions can be evaluated using the substitution. So we have u that is equal to e raised to x is also equal to x is equal to the ln of u, wherein dx is equal to du over u. So for the first example, we have the integral of the hyperbolic sine 1/2 x dx. So using the u substitution, our u is equal to 1/2 x. And the derivative of u is also 1/2 dx. So in this example, we're going to use or to have the correction factor because on our original example, we don't have 1/2 here. Okay, so we're going to add 1/2 and get the reciprocal or the inverse of 1/2, which is 2. So this is our new function. So 2 integral of 1/2 hyperbolic sine 1/2 x dx. Then using the u substitution, and we have our 1/2 sine is the u, and our 1/2 dx is du. Then getting the integral of the 1/2 u du, we have the 2 hyperbolic cosine 1/2 x plus c. So that is the final answer. The second example is to evaluate the integral of the hyperbolic sine squared x dx. So here in this example, we're going to combine the identities. So as you can see, we use the Pythagorean theorem. So we have the hyperbolic cosine squared x minus the hyperbolic sine squared x is equal to 1. Okay, combining the identity of the hyperbolic cosine 2x is equal to the hyperbolic cosine squared x plus the hyperbolic sine squared x. So we can write that one as the hyperbolic cosine 2x is equal to the hyperbolic cosine squared x plus the hyperbolic sine squared x. So as we combine them, we have the 1 plus the sine or the hyperbolic sine squared x plus the hyperbolic sine squared x. So we have the same function. So we're going to combine them. So we have 2 times the hyperbolic sine squared x, or simply as 1 plus 2 times the hyperbolic sine squared x. So that would be our new function of the hyperbolic identity. Yeah, so in this part, we're going also to use the half angle formula. So what would be the formula for the half angle? So we have the hyperbolic sine squared x is equal to the 1/2 of the hyperbolic cosine 2x minus 1. So going back on our original given, okay, the integral of the hyperbolic sine squared x dx. Then following this half angle formula, we have 1/2 the integral of the hyperbolic cosine 2x minus 1 dx. Then getting the integral of this part, we have the hyperbolic sine 2x over 2 minus x plus the arbitrary constant. Then by simplifying them, we have 1/4 times the hyperbolic sine 2x minus x over 2 plus c. And another part is a general power formula. So it is given by the d over dx times the f of x raised to n plus 1 over the n plus 1 plus c. So for that example, evaluate integral of sine raised to 1/3 x cosine x dx. So using the u substitution, our u is equal to the sine x, and the derivative of u is a cosine x dx. So we have the integral of u, based on our u substitution, 1/3, and our cosine x dx replaced into du. Then applying the integral of this function, we have the 3 sine raised to 4 over 3x over 4 plus c. So as you remember, on the basic rule, we're going to add 1 on the exponent, and if what would be the sum of that exponent would be the denominator of this function. So we come up in this answer. And next topic is a definite integral. On the previous slides, it is all about the indefinite integral. So when we say definite integral, it has start and end values. In other words, there is an interval a and b, or a and b called limits, bounds, or boundaries, are put at the bottom and top of the S like this one. So we have the two types of the integral, the definite and the indefinite integral. So example for the definite integral, evaluate the integral of 4 dx from -3 to 5. Our lower boundary is -3 and our upper boundary is 5. In getting the integral of the definite function, we're going to subtract the lower integral, the lower boundary to the upper boundary. So we have 4 times the difference of the upper and the lower. So we have 4 times 8, and that is equal to 32. So that is the definite value of this given integral. And next example, evaluate the integral of 3x squared minus 5x plus 2 dx from 1 to 3. So as you can see, we separate the first term, second term, and the third term for us to easily find or get the integral. So we have the integral of the first term, which is 3x squared dx from 1 to 3, minus the integral of 5x dx from 1 to 3, plus the integral of 2 dx from 1 to 3. So as you can see, we can apply the constant multiple rule by separating the constant into the variable. So we have the 3 integral of x squared dx from 1 to 3 minus 5 the integral of x dx from 1 to 3 plus, so in this part, we get directly the integral of 2 from 1 to 3. By adding the upper and the lower boundary. So that is equal to 3 minus 1, correction for that, 3 minus 1 is equal to 2 times 2, that is equal to 4. And again, in getting the integral or applying the integral indefinite function, we're going to get the difference of the upper and the lower boundary. And then now, And we're going to get the other integral of the other term. Yeah, so we have the 3 times 26 over 3 minus 5 times 4, okay, plus 4, that is equal to 10. So that is a definite integral of our given function. That would be all. Thank you and see you on our next video lecture.
For more ICCT College's video updates, please subscribe and click the notification button.